This video is looking at the group 7 element, also known as the halogen. So just to put this into context, this is part of C4 of the GCSE chemistry course for OCR, and you have the alkali metal, so there's a video on that, and this is following on with the group 7 elements. There's also group 8 elements in this topic, and then transition metals. And there's going to be quite a lot of crossover between what we talk about here and what we also talk about in the transition metals. First, let's start with the halogens that you're expected to know about. So the first halogen that you're expected to know about is chlorine. It isn't actually at the top of the group. Above chlorine, we have the element fluorine, which is at the top of the group, but fluorine is even more reactive than chlorine. And so, as the opposite of group 1 metals, the group 7 element, the halogens, get more reactive as you go up the group. Nevertheless, we have to study chlorine. So chlorine is a green gas, as you can see here. Obviously, it's difficult to see the green colour, but it is pale green. Think of chloro within chlorophyll or chloroplasts, the green part of the plant. It's used to sterilise water. So in C6, you need to know that the third stage of purification of water is chlorination, and we use that chlorine to kill harmful bacteria to make water safe to drink, or to make it safe to swim in and get swimming pools. We also use it to make pesticides and plastics, such as PVC. Now, bromine is the next halogen, and bromine is an orangey liquid. In fact, the bromine in this container is here at the bottom. Now, the boiling point of bromine is very close to room temperature, so it turns into a vapor very, very easily. So if we're just comparing these two, chlorine is a smaller element than bromine. So as you go down the group, the molecules get bigger. So if I was comparing two molecules of bromine, there are simply more intermolecular forces between them than if I had much smaller molecules of chlorine. So the boiling point is one of the trends that you've got to be able to explain for halogens, and the boiling point increases as you go down the group. So as you go down the group, the boiling point gets bigger. So that's because the intermolecular forces increase. So chlorine is a gas, but bromine has a higher boiling point and therefore is a liquid. Bromine is used for flame proofing, to make pesticides, and also to make medicines and dyes. Now the next one is iodine. So iodine continues this trend that we've just talked about with boiling point increasing, and you can see that iodine is a grey solid. So this is iodine. Iodine has a unique property that when it's warmed, it misses out the liquid state altogether and goes straight from a solid straight to a gas, and that process is called sublimation. The use of iodine is it's used as an antiseptic. It's used to sterilise wounds. Now, things that these molecules have got in common is they all react in the same way. So they react with metals quite vigorously, and they form metal halide. So all that means is the name of the halogen is changed to "ide" at the end. So for example, this reaction here is actually potassium, which is on the spoon here, reacting with chlorine to form potassium chloride. And when the halogens react, they all do the same thing. They all lose their electron in their outer shell. So for example, chlorine's electron configuration is 287. It has 7 electrons in its outer shell. I apologise, I just said it loses electrons, I mean it gains an electron. So you can see it goes to 7. So what it wants to do is it wants to turn into 288. Okay, and by doing that, it becomes negative. It has a -1 charge. So all of the halogens, when they react, they gain an electron. And oxidation is loss and reduction is gain. So they're always reduced. So for example, chlorine, okay, when it reacts, is going to gain an electron. And because I've got 2 chlorine atoms in a molecule, because it's diatomic, and all of the halogens, when you write them as an element, always have to have this 2 here. They are all diatomic. So di meaning 2, obviously atoms being atoms, so diatomic means 2 atoms. So each of the chlorine atoms will gain an electron, so I need 2 electrons, and that will give me 2 chlorine -1 ions, okay, or chlorine anions. So just a couple of examples of this. So any metal in a halogen will give us a metal halide. So one example would be sodium as a metal plus chlorine as a gas. So obviously, as I put the state symbols, sodium would be a solid, chlorine would be a gas, and then I will form sodium, which is +1, and chlorine, which is -1. So the formula of NaCl, sodium chloride, is just NaCl. That would be a solid, and I need to balance this. So because I've got 2 chlorines here, I need to put a 2 there. That means I've got 2 sodiums, so I need to put 2 there. So sodium plus chlorine gives me sodium chloride. That would be one example, but this works for any metal and any halogen. So aluminium and bromine gives me aluminium bromide. Potassium and iodine gives me potassium iodide, etc. But in every single case, to reiterate the main point, is that the halogen, when it reacts, is going to gain an electron in its outer shell, and it is going to form a chlorine or a halogen -1 ion. Very important that you understand that they all gain 1 electron to fill their outer shell. That is why as you go down the halogens, the reactivity decreases, because it's easier to gain an electron when your atom is very small. This is the exact opposite of the group 1 metals, where the reactivity increases down the group because it's easier to lose an electron. So moving on from that then, the other reaction that we need to know for the halogens is their displacement reactions. And displacement reactions, if I skip to the definition, is when a more reactive element displaces or swaps with a less reactive element. So if we were to carry this out experimentally, we have our 3 elements here, iodine, bromine, chlorine. Now just to give you an idea of colours for these, and these are all in solution. So these are the halogens, not in their pure form, but dissolved. So all AQ. Okay, so remember AQ for aqueous. That is in solution. So chlorine is a very, very pale green. So pale, it's barely green at all, but very, very pale green solution. The bromine is a very, very pale yellow colour, and again it's very, very pale. Iodine is orangey brown, and this is in solution. I just want to reiterate that's the solutions, not the elements. The element, yes, chlorine is a green gas, but in solution it's also very pale green. Bromine is normally an orangey brown liquid, but in solution it forms a yellow solution. Iodine is normally a grey solid, but in solution forms an orangey brown solution. That's what we'd see. So if I react these with these compounds, we'll see what would happen. So the controls would all be these colours as a reference. And then if I react with chlorine with potassium iodide, chlorine is more reactive than iodine. So what the chlorine can do is it can swap with the iodine and form potassium chloride, and I'd be left with iodine. So what I would see in this case is my solution would turn from green to orangey brown as the chlorine swaps with the iodine. The iodine is left in solution. Chlorine is also higher up than bromine, so that will also react, but this time we'd see the solution turn yellow. Obviously chlorine can't displace itself, so that wouldn't react. Bromine is more reactive than iodine as well, so it would also be able to react, and again the solution would go orangey brown as the bromine swaps with the iodine. The iodine is left in solution. Obviously bromine doesn't react with itself, and bromine can't displace chlorine because it is lower down the group. And obviously iodine, being at the bottom of the group, can't displace any of the other molecules. It could displace astatine, which is right at the bottom of the group 7 elements. So this is how we did test and investigate the group 7 halogen reactions. We react the halogens in solution with halogens as a compound, and if it's more reactive it will swap. Remember, the reactivity is highest at the top of the group. So the only element that could displace chlorine would be fluorine, which is right at the top of the halogens. So this is what a displacement reaction is. Very important you know this, because this is the bit that crops up a lot in transition metals. So just a generic example of one of these reactions, and these are really simple because they're always the same. So if I start with chlorine, okay, and that is in solution, so it's AQ, okay, and I react that with, for example, it doesn't really matter what the metal is, but if we just do sodium, and we'll go for sodium bromide, again, that is in solution, so AQ. What will happen is the chlorine, because it's more reactive than bromine, will swap places. So you will have sodium chloride in solution. So the solution will lose its pale green colour because the chlorine is now in the compound, and we will be left with bromine in solution. And bromine is a halogen, so just like chlorine, it always has to have a little 2 after it. Again, AQ, because it's in solution. So in order to balance this, remember, anything that doesn't have a 2 in it, put a 2 in front of it. That would balance. And that works for any halogen displacement. If it was sodium iodide, it would be chlorine plus 2 NaI goes to 2 NaCl plus I2. So it would work exactly the same way if it was iodine. Bromine could also do this. And I won't include the state symbols this time. I will just do this quickly. So bromine, let's just pretend it's a different metal. So potassium iodide, for example, bromine is more reactive than iodine. So it would swap, and I'd get potassium bromide, and I'd be left with iodine. Okay, but again, balance it by putting a 2 in front of everything that doesn't have a 2 there already. So obviously, state symbols are all in solution. So this is the halogen displacement reactions. Remember, the more reactive the element, the ones at the top of the group are most reactive, they can displace the lower down, less reactive halogens.